Alright, so this video is on AP Physics C 2024 E&M Set 1 FRQ 3. Interesting question. A wire is connected to a resistor of resistance R to form a rigid rectangular loop of width L and height 2L. External force is from the loop so that the loop always moves with a constant speed V in the x plus x direction. So loop enters the region 1 of external uniform magnetic field of B that is directed into the plane, so minus the axis. Region 1 L, this is just 2.5, that's all they have mentioned over here. Nothing too nothing too much to pay attention to. These are just instructions, pretty much intuitive from the figure, and assess the midpoint. Okay, what do we need to find? On the following axis, sketch a graph of the magnetic flux through the rectangular loop as a function of the position x from x equal to 0 to 4.5 L, and the plus direction is corresponds to plus phi, so positive flux is towards the plus x direction. So let me quickly borrow this figure over on the same slide. Okay, I think that should be okay, or maybe a little bit. Okay, that's fine. Okay, so the first thing which we notice is as soon as it enters, by the way, from 0 to L, there is no flux. What is the flux, by the way? Let's remember flux again. Flux is B dot A, or B A cosine of theta, right? B A cosine of theta. And we know that the plus Z direction indicates a positive flux. So we don't really have to worry about this theta because the sign is pretty much dependent on the direction of the magnetic field, uh, 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 you know, and the plus Z is anyway taken as the positive sign. So what we're going to have over here is from 0 to L, by the way, there is no flux because there is no magnetic field. So I know that this is going to be 0. Let me draw with a free hand. This is going to be 0 till this point. After that, flux is going to increase, but increase in which direction? I think the negative direction, because this is B is pointing out of the, sorry, A area vector is pointing out of the page, magnetic field is pointing into the page. So that's going to be in the, and in fact, no need to, like I said, no need to pay attention to this one because they are saying that the plus Z axis indicated in figure 1 corresponds to positive flux. So obviously, this is going to be the negative flux because this over here in region 1, it is pointing in the negative Z direction. So this is going to be negative flux. So we know that it's going to be below the X axis. And till 2L, we need to find that first. So I know that since it is moving forward with a constant velocity, so area, let's say the curve, that let's say this much loop is inside the magnetic field. So the rate at which the area is increasing is also linear, right? Because magnetic field is constant, whatever that is. Area is width, length, which is 2L, which is not changing, times width. And the width is continuously increasing as a function of time because it's constant velocity. So V times T, right? V times T, that's going to be the velocity over, that's going to be the length over here. So with time, it is definitely increasing linearly, or we can say that it is proportional to x because we are graphing with respect to x. So if it is, inside by x units, so it is increasing linearly. It is increasing, but in the negative direction, remember? So it will increase on and on and on till some point 2L, so that there will be a straight line, something like this, till 2L. Okay. Now, when the right edge of the loop is at 2L, let me clear this thing now. Don't you think the loop is completely into the magnetic field because the loop has a width of L and this is 2L. So from this point to this point, which is 2L to 2.5L, the flux is going to be constant because neither the area inside the field is changing nor the magnetic field is changing. So whatever it has attained, that's going to remain constant till 2.5. And after 2.5, don't you think the flux is going to be 0? That's what I think, because as soon as it starts penetrating into it, oh no, it's No, it's not going to be 0 because the left edge is still having some magnetic field. Okay, that's interesting. Let's try to draw this curve once again. As of now, the field, the loop was completely inside, so it was something like this. Uh, and at 2.5, in fact, I'm sorry, I'm interested at 2.5. So when it is at 2.5, this will be 1.5. So it will be like this. Uh, yeah, so this is going to be L and this is going to be 2.5 L. So the moment the loop now moves forward, at least the right portion, the portion which is in the region 2, that's not going to have any magnetic flux because the positive field and the negative magnetic fields cancel out each other. Essentially, there is no field here. So if there is no field, obviously there is no magnetic field because that is of the same magnitude, right? Correct. That is of the same magnitude. Yeah, same magnitude, different direction. But still, there will be some part of the loop which is in the region 1 as well. And that will happen till the entire L enters the region 2. And region 2 is also of L width because it's from 2.5 to 3.5. So this is what we have. But in this case, the flux is going to approach to 0, right? 0, because after all, the length is now, the loop is coming out of region 1. So till 3.5, the loop will once again, from the same slope, it will come out to, it will come to 0. And once the loop is entirely in region 3, I think when it moves forward, again the flux is going to be 0 because some part or some portion of the loop is in region 2, which is already 0. And the other portion is still is in the region where there is no magnetic field. So till 4L, it is going to be 0. In fact, till 4.5L as well, it is going to be 0. So this is how the flux should look like. So this makes sense. The next one which we have is consider the instant when the point S reaches 1.5L. So again, I'm going to borrow this. Now they are asking us to consider the instance when the point S reaches 1.5 S. So 1.5 S is here, right? So 1.5 means half inside, half outside, like this. Sorry, it will start from here. Okay, all right. This is what it is. Half inside, half outside. Now they're saying that indicate whether the is clockwise, counterclockwise. So that's easy. That's easy because that's Lenz's law straight away. We can see that when it penetrates into region 1, what is happening? Its magnetic flux is increasing into the page, right? And what does Lenz say? Lenz says that the induced magnetic field, the induced magnetic current or EMF should oppose the cause. What is the cause? The increasing magnetic field in the negative z direction. So to counter something which is in minus z, it should induce a magnetic field in plus z. And if you want to induce something which is in plus z, you should the current should flow in counterclockwise sense, because if the current is like this, then using the right hand rule, if you take your right hand and curl your fingers towards the counterclockwise sense, your thumb is pointing out of the page, which is going to give you the induced magnetic field, which is exactly what we want, right? Oppose the cause, oppose the cause. So we are opposing when we are in counterclockwise sense. So this should be the answer. Justification is definitely oppose the cause. So you can just say that induced EMF is minus of d phi over dt, since the flux is increasing in the negative z direction. So the minus of z is the positive z direction. Positive z direction would mean that the current should be in counterclockwise sense as per the right hand curl rule. Right hand curl. Okay. Write an expression for the induced current when point S reaches this. If IR is 0, indicate how the derived expression shows IR is 0. Determine the answer in terms of this and physical constants. Okay, all right. So if we want to find the current at this point. So the induced current, for that we need the induced EMF, right? So induced EMF, since we are talking about the magnitude, I'm just gonna say that this is equal to d phi over dt. What is flux? Flux is B dot A or BA cosine of theta. Cosine theta is again ignored because we are just interested in magnitude, and theta is 180. 180 is minus 1. Minus is ignored. So I hope you understand that. It's just BA. And B comes out, it's a constant. So we are just left with B times dA over dt. And what is going to be the area? I mean, I can again pull that up. The area is going to be length, which is 2L, which is going to be constant. So d over dt of a constant 2A times whatever it has penetrated, inside, which is just x, right? So this is going to be equal to the EMF, the induced EMF, let's call it E induced, is equal to, or let's say ER is equal to B times 2A comes out. Sorry, why is this 2A? This should be 2L, right? Okay. This should be 2L. And this thing should be, sorry, I need to correct here as well, 2L. And then I'm left with dx over dt. And what is dx over dt? Isn't that velocity? And what is velocity? That's just v. So 2BLV, that's going to be the induced EMF, but they are interested in the induced current, so that's not a problem because the induced current is just the EMF over resistance as per the Ohm's law. So that's going to be 2BVL over R because that is the resistance over here. So that should be the derivation of the current. Right, let's talk about the next one. Derive an expression for the power P dissipated by the resistor when S reaches this. Okay, so power is also given by what? I square R. In fact, this can be written as V induced square over R. What is V square? I think we just derived the V, right? So that's going to be the induced EMF is already derived, which is 2BVL. So I'm just going to take 2BVL whole square over R. So that's going to be 4B square V square L square over R square. So that's going to be our answer for the induced power dissipated. You could have used the I square R as well, guys. It's totally fine. That will still give you the same answer, so don't worry about that. Okay, now they're saying that the total energy dissipated by the resistor when it moves from 0 to 4.5 L is E original. Okay. E original. Okay, all right. Now the vertical boundary of region 1 and region 2 is now shifted, right, to 1.5 L. So which means that initially it was, again, I can pull this up for you so that you can see everything in a single view. So initially it was starting from 2.5 L. The region 2 was starting from 2.5 L, and now it's starting from 1.5 L. The rectangular loop again moves with the induced EMF is now E nu. So indicate whether the E nu is greater, less, or equal to the original energy. I think that's going to be less. That's my prima facie answer, with a very simple fact that now there is less region to induce EMF in, because it will only travel for 0.5 L, and then in this entire region there is no induced EMF. So there is no induced EMF means there is no induced current, and no induced current means no induced power. So that is, I think, my rationale, that less power means less energy. Less energy would mean that E nu is going to be less than E or. So that is what I think should be the case over here. So I'm going to say that the power is only dissipated when the flux is changing. And since the flux is changing now for a shorter duration, which is only this much, so the E nu is less than E origin. Right. I hope this makes sense. The next one is, in fact, the last part. The original magnetic fields are modified so that L to 2.5, 3.5 L contains only Oh, well, that's a relief. Only going into the page. A new wire is now connected. Okay, that is an interesting wire that is being triangular loop with da 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 da. It's again moves with a constant speed v, and on the following axis, sketch the induced current in the triangular loop as S moves from L to 3L. Okay, okay, all right. Um, I think it's easier to first determine where there is no induced current, I would say, because again, this is L. So as soon as the left edge of the loop is over here, it's over here. So the other L will come over here. So when the right edge of the loop or point S has moved to 2L, then till 2L to 3.5L. Oh, sorry. Okay, we just need to graph from L to 3L. So that's a relief because from 2L to 3L, there's essentially no EMF because it is just into the same magnetic field. Area is not changing. So that's a relief that at least this portion is just coming as zero, right? Okay, all right. Now it's all about area. We need to find how the area is changing. Is that still linear or is that quadratic or something like that? So if we were to draw a portion, let me replicate this situation over here and try to do some geometry. Let's say this is the region which is into the page, and the moment it enters, I'm going to remove the resistor here because that's just not playing any part in the graph. So let's say the triangular loop is now something like this, slightly penetrated inside. And this is the edge, uh, you know, the dotted line which represents that the magnetic field starts from here. So this region is into the magnetic field. I think both height and width are changing. So I know that this is 2L and this is L. So let's say this has entered with a distance of L, this is distance of X, which makes sense, but we don't know this. But it's easy, right? These are symmetric triangles. Which one are symmetric triangles, guys? This bigger one and the smaller one. I'm sorry. Yeah, a smaller one. Yeah. These are symmetric triangles. So what happens with symmetric triangles? The ratio of the corresponding sides are equal. So we're going to say that 2L over L should be equal to Y over X. L and L is gone. So 2 is equal to Y over X. So Y is equal to 2X if we just flip the omelet. So if Y is 2X, then what is the area of this triangle, guys? Because that's what all matters, right? So the area of this shaded portion is going to be half times base times height. So that's just going to, sorry, it's just 2x. So 2 and 2 is gone. So that's going to be x squared. Whoa, it's not linear. It's not linear, definitely. It's not linear. So that's going to be a parabolic curve, and that parabolic curve is actually increasing with time. So that's going to be, I would say, and by the way, this is area only. This is area only. So first, let's find the flux. In fact, can we just use the equation which we derived earlier? The current was, oh no, we cannot, right? Because the area was something else. So, okay, I think I believe we might need to derive this quickly. So I know that the EMF is again minus of, or just the magnitude is d phi over dt. So d over dt of flux, the flux is b dot a, and the area is just x squared. So the derivative of this is going to be 2x times b times dx over dt as per the implicit differentiate, the derivation and the chain rule, and dx over dt is just v. So it's 2bv x over here, 2bv x over here. There is no L. So definitely the EMF is dependent on X. Obviously the current will be in the same fashion. It will just be, the only difference will be, it will be 2bVx over R. So that's going to be a linear increase now. The current, the area is definitely X square, but the flux is going to increase linearly, and the current, induced current, is going to increase linearly. So it will increase linearly till some point. and then it's just going to drop to 0, and that's how it should look like. You can also represent this sudden drop by a dotted portion. So if you want, you can just represent with some dots as well. It will maybe make more sense. So it's the dotted portion over here, and that it becomes 0. Well, this makes sense. It was a little challenging, but yeah, this is how we solve it. Any questions, please post it down in the comment section. I'll see you in the next video. Bye-bye.